So what this is the initial review of our treatment plant study. In 2024, we secured some funds from the state of Michigan to go ahead and have a study of the treatment plant. We are, I think, 2 years out from our 100th anniversary of making water on that site. There's some upgrades that need to happen to that building, and kind of the goal of this whole thing is to be able to lay out, do we retrofit our current site? Do we go somewhere else? Do we do something halfway in between? While they don't build plants as pretty as that anymore that we have, there are some structural things just by the layout of the treatment plant that are going to need to get changed at some point in time. And one of the big goals on this study is to go ahead and capture all those potential costs, so that when we lay that out to everybody, that it's whatever $1 million to do this or whatever $1 million to do that, everybody knows what we're looking at and what we're up against. So that's the reason for the study. We want to make sure we're setting the table, so that 100 years from now, somebody else is sitting here saying, okay, now that retrofit you all did 100 years ago worked awesome, what are we doing next? So that's kind of the view that we're taking.
So the evaluation that we're currently completing, there's really nine tasks that make that up. Project kickoff, data review, stakeholder engagement, that's what we're starting on today with this meeting. There's a water reliability study that's gotten combined with this water plant project. A regulatory compliance analysis. We've done an existing plant condition assessment. We're currently doing some alternative review and process selection and alternative evaluation. There'll be some repurposing concepts that we look at for the existing building, and then there's kind of a wrap-up reporting, cost estimating, construction planning phase. I'll kind of give you an update on where we're at with all those tasks right now. That first task, we've completed that. We've got all the background data, kicked the project off back in 2024. Stakeholder engagement, again, this is the first set of public engagement meetings that we're doing. On the water reliability study, we've got the model. We've been making updates to the model. We're kind of in the midst of calibration. Did field work for that this spring, hydrant flow testing and that type of thing. And then we're going to use that model for the rest of the reliability study. Task 4, that regulatory compliance, we've got that completed. The condition assessment of the existing plant, that's done. Really the kind of the meat of the project, the alternative review, process selection, alternative evaluation, that's what we're in the middle of right now. Repurposing concepts, just done a little bit on that so far. And similar with the reporting and cost estimates, that's just getting rolling. I'll kind of hit some key items from the different tasks that I thought would be of most interest. The reliability study there, part of the reliability study is to do water usage projections. That informs the reliability study. Also, the plant study relies on this data. So the projections looking at population and growth trends are showing moderate growth over the planning period. The middle set of data there on the graph, the orange series and the blue series, that's our maximum daily demand, and that's really what is most important for sizing plant components. So projecting that maximum day demand out 20 years to 2045, we're looking at just over 30 MGD. Contractually, if you add up all the contracts that the city's committed to, that comes out to 38 MGD, and the actual plant capacity now is 52 MGD. So the question is, should we maintain 52 MGD, have that in reserve for future needs, or should we downsize the plant and reduce the capacity to something maybe closer to that 38 MGD? Obviously, there's big dollars that go along with each of those MGD if you can find some savings there. Regulatory compliance analysis, there's a few things that go into that. The plant is currently compliant with all the regs, looking as best we can at what we think is coming down the line in the future. We don't anticipate any issues there. We see compliance with the future regs. One important thing there is We haven't seen PFAS or forever chemicals in the water, so that's a positive. And there are new technologies that can be more efficient and cost-effective in meeting these regs. We do know disinfection byproducts are a challenge, particularly for some of the customer systems that are further out with a longer water age. So that's something we'll be looking at. And then we've got the ongoing corrosion optimization study. We've got pipe loop setup that's in the basement of the plant. This is a picture of that where we've tested lead and copper piping for corrosion optimization. That's kind of a parallel study to the one we're talking about today. The existing plant condition assessment. So like I mentioned, we completed site visits in 2024, got a team of engineers out here, structural engineers, mechanical engineers, electrical engineers, and we looked at all the plant systems. The treatment equipment was one of the major focuses. The building itself and the condition of the building was something we took a close look at. And then the building mechanical systems and electrical systems, and then the mechanical and electrical systems that support the process equipment. And then another key item we looked at was the structural integrity of the building. The overall assessment, the structures are in good condition, relatively minor repairs needed to keep those up to date. The building and the equipment in the building has been well maintained. Some of that equipment is, you got pumps that are original, 100 years old to the plant, still operating well. That's a testament to the people that have operated this plant for decades, doing a good job on maintenance. Despite that great effort towards maintenance, a lot of the equipment is really old, needs replacement either due to age or obsolescence. There's new, better equipment out there now. Just some highlights of some of the needs that we saw at the plant. The valves, sluice gates, valve actuators, that type of thing, that are used to direct flow between different parts of the plant or isolate processes. Those, for the most part, all need to be replaced. The whole high service pumping system, the pumps that deliver the water to your distribution system, that either needs a major upgrade or a complete replacement. The chemical feed systems that deliver the chlorine and that type of thing to the system are in need of replacement. The traveling screen, that's something that screens the water coming into the plant to make sure you don't get fish or big particles coming into the plant. There's a picture of that there. A lot of corrosion on there, some issues with that piece of equipment that needs replacement. Other replacement needs, the sanitary and storm drains that are within the plant need to be separated from each other so that you don't have the combined sanitary and storm flows. The electrical service from the electrical utility coming to the plant needs to be upsized. Electrical switch gear that delivers the power throughout the plant and the motor control centers, that type of thing, all needs to be replaced due to age. We've got a picture here of the boilers that heat the plant. They're old and need to be replaced. We've got a lot of leaky windows in the plant that need to be replaced pretty much throughout the plant. There's an area and the transition from the 1927 bank of filters to the 1964 filters where a little bit of differential settlement and some cracking going on. That's allowed some moisture infiltration, some groundwater, et cetera, from the outside coming in. That's a spot that needs to be repaired. We've got a picture here of one example of concrete that needs to be repaired. You can see the spalled concrete and exposed rebar, the resteel that is within the concrete. That's on the rapid mix riser structure in the plant. That's just one example of something that needs to be fixed. I mean, the fix on that is relatively minor, but if you allow that to go for too long, you're just going to get more structural damage. That rebar, when it starts to corrode, can basically expand and pop the concrete off the structure. Kind of a summary of needs. Like I said, we did a comprehensive look at the plant. We've got about an 80-page report that summarizes everything we came up with. There are about 60 items identified. Some of those are specific things like we talked about here. Some of those are complete systems that need to be replaced. So we looked at maybe a dozen of those 60 items briefly today. The overall assessment was that the building, the structures, the big stuff was in good condition, needs some work in some areas to extend the life of that, but we believe there's significant remaining life, useful life in that plant. There are some needs that are going to be really challenging to address. The first one I'll highlight here is the central gatehouse flow splitting structure shown on the slide here. There are several large pipes that come together, 48-inch pipe, 60-inch pipe, into this common splitting structure. And there are ways by opening gates to direct flow from one set of tanks to another. This was okay when it went in 100 years ago. There's a potential if you open the wrong gate, you could send lower quality water into a tank or process that has higher quality water and basically degrade the quality of that water. That's something that Eagle's identified as a risk for the plant, and they're requiring replacement or modification of this structure. The issue there is this thing is 20 feet down in the ground. It's part of an existing building, not a good way to get at it. So figuring out how to retrofit this, how to fix this problem is a challenge. It's something we're noodling on but haven't figured out yet. That kind of leads to another thought. You got these large pipes out in the yard. Some of them are kind of right next to each other. All that pipe, if we're going to go another 100 years here, really needs to be replaced. But trying to put new pipe in the ground while you've got the existing pipe in service is really challenging, particularly when you look at the amount of space that's available.
The challenge of digging on a 100-year-old site is it's like digging in a bowl of spaghetti. So while we have prints on our pipes, sometimes somebody in 1928 forgot to write something down, and then 1963 and so there's the most recent one, and this just literally came up a couple of weeks ago, we found a bunch of stormwater piping that was not on a single print that we had. It all needed to get replaced, and we had no idea it was there until we dug it up. When you're working on an old site like that, you've got a lot of things that were okay back in the day, but are no longer okay, and things that just nobody wrote down.
Last bullet here, Mike mentioned the storm and sanitary piping. Outside in the yard, we've also got situations within the building where that needs to be separated. But the existing pipes are, cast into the walls of the building, cast into the floors of the building. Fixing that is another difficult challenge.
So now I'm going to talk about process selection, and I want to back up a little bit just so I don't want to use a bunch of jargon here. So when we think about a process in a water plant, you can think of it as like a bunch of equipment that works together to do something. Like if you think of a car, the car has an engine, right? It has transmission, it has suspension, other things, right? And all of those are made of different equipment, but they all kind of work together. Like the engine provides power for the car, the transmission transmits it to the wheels, the suspension kind of keeps it on going down the road straight and keeps you from getting jostled too much. So in a water plant, we can kind of break down the equipment into different processes. So what we're doing as part of this project is trying to come up with what processes do we want to use to either upgrade the new plant or build a new facility to set the city up for the next 50 or 100 years of treatment. And we want to make sure whatever we pick is cost effective, that it's flexible, that if something like Eagle is Michigan's environmental protection agency, or the federal environmental protection agency, if they change something, that either we can treat it in the plant or we know what to do so that we can meet that challenge. And we know the existing water plant, like Mike was saying earlier, it's this water treatment castle, right? It's important to the community. We were up here for Christmas last year. It's really, it looks cool. The Christmas celebration there is really neat. So we know that whatever we do, that facility's got to be maintained for the community. And Dave's going to talk later about if we do go with the option of maybe building a new facility, how we are going to look at options for using the existing plant for the benefit of the community. So just real quick, if you're not familiar with how where your water comes from and how it gets treated, most of the water that you drink in Saginaw and the surrounding communities. It comes from Lake Huron up at Whitestone Point. So it's quite a ways away, right? So we pump water down here to Saginaw. Because we don't want to just have all our eggs in one basket, we've got a couple of backup water supplies. So there's a couple of reservoirs up in Kochville Township. If you look at like Google Earth and you see two like, they actually look like squares like that. If you see those are your backup water supply for the city. There's also Lake Linton, which is not too far away from here. So once water gets pumped from the lake, it goes into basically a big mixer where we add chemicals that help address taste and smell issues. So PAC is powder activated carbon. If you've heard of activated carbon before, if you haven't, it's what's in like fridge filters or like Brita pitchers. It can take out organic material. It can take out kind of funny tastes and weird smells. And then we add some other chemicals that take all the little stuff in the water. Like if you scoop water out of Lake Huron, right, it looks clear, but we know there's stuff in there. It's bacteria and viruses and other things that we don't want to drink. So we add chemicals, we call them coagulants. And basically what they do is they take those little particles that want to float around and help them to stick together into big clumps. And then once we start sticking them together in the big clumps after we add the chemicals and mix it in, we go through a slow mix process where it just kind of gently mixes the water to help make those clumps bigger and bigger. And then it moves on to settling tanks. So it's just basically a big open vat where water moves really slowly. And those particles can settle out. So you take out a lot of the stuff that's in the water you don't want to drink. And then to polish it, we go through filters. So it's basically, think of like a 3-foot deep sandbox, basically. And those take out most of the rest of the particles that are in there. We add a little bit more chlorine to disinfect the water, and then it goes out to you in the city to drink. So for our upgrades, we're looking at this in the context of like, what do we need to do with our water plant to kind of pick a set of processes that are going to provide the same or probably a better level of treatment, but still be cost effective. And kind of big picture, this slide here has all the different things that we need to think about when we're thinking about treating water. So the big, most important thing that the water plant does is it gets rid of viruses and bacteria and like, have you ever heard of cryptosporidium? I don't know if anyone was around in the 90s. In Milwaukee, a lot of people got sick from that. The most important thing a water plant does is to get that stuff out of the water so people don't get sick. So maintaining, we call them pathogens, right? Maintaining pathogen-free water is the most important function of the water plant. We also are focused on minimizing lead and copper. There's things we can do in the treatment process that help with that, and I believe, Mike, the city is in the process of removing lead service lines, so that becomes less and less of an issue over time. Managing something Dave mentioned earlier, disinfection byproducts, or DBPs. Like I said, we need to kill those bacteria and stuff that make people sick, right? So we use chlorine to do that. The problem with chlorine is that it's really, really good at killing bacteria and viruses, but there's other organic stuff in the water, and when chlorine reacts with that, it can form some chemicals that aren't very good for us. So one of our goals is to minimize the amount of that forms in the water. There's already processes in the existing plant that help with that, but that's going to be one of our key things, is to keep those levels low for the consumers that are drinking the water. A couple other things we want to be prepared for that aren't necessarily current issues are cyanotoxins. So sometimes algae or blue-green algae can release things in the water that are also not good for us. We haven't had, I believe, any detections of that yet in Saginaw, but we know other communities in the U.S. have seen those, so usually it's not a problem until it is, so we want to make sure we've got flexibility built in to address that. Manganese is something that can cause fixture staining and other issues, and that's something that could come from like the reservoir sources, so we want to make sure we're prepared to address that. And then once we've dealt with all the health-based things, we know people nobody likes gross water, right? So keeping water that, tastes and smells good is another priority for us. So these are the overall goals that we're going to use to drive what processes that we pick for either the upgraded plant or a new facility. I'll talk about a couple of technology options now, but everything is on the table. And we're looking at how can we put something together that is going to be compliant, it's going to produce high quality water, and it's also going to be cost effective. So I'll give a couple examples of some of the things we're looking at. So first is the pre-treatment. So right now it's conventional coagulation, flocculation, and then sedimentation in open basins. So it works well, but it takes a pretty large surface area. So a couple of alternatives we're looking at are using plate settlers or potentially using dissolved air flotation. So plate settlers are basically you put inclined, picture a bunch of plates, a few inches apart, about 60 degrees angle, and basically you can dramatically increase the settling capacity of your existing basins by just dropping those in. So that gives us the ability, if we retrofit the existing plant especially, to maintain production and also kind of strategically retire some of the older assets of the plant. Like you may have seen earlier, the plant has two sets of settling basins, like first set we call the clarifiers, and second settling basins. If you put plates into one of those, you can potentially eliminate the other one, which can free up some space on the plant site, and also potentially make it easier, reduce maintenance costs because you don't have another structure that needs to be maintained. Another advantage, if we go with the new plant route, is it cuts the footprint by about half, and that's a huge savings in terms of concrete and steel. Another alternative is dissolved air flotation. So basically, instead of settling out flock, we float it instead. So it's like opening a can of pop, right? In a can of pop, you got carbon dioxide under pressure, or like picture a clear bottle, right? And when you open it up, you can see all the bubbles. You can do the same thing in water treatment. You dissolve air into water under pressure, and then if you release it through just the right size nozzle, you can see it. It's the milky looking picture over there. So those little tiny bubbles can attach to the flock and float it, and you can reduce your footprint to probably about 35-ish% of a conventional basin. So again, it's looking at ways to make a new facility or even an upgrade more cost effective by using things that are more efficient and can do the same kind of work in a smaller footprint. For filtration, we're looking at both granular media filters and membranes. And you may be wondering, membranes are the hot thing, right? So why are we still looking at granular media filtration? And the answer is that granular media filtration has a lot of flexibility that membranes don't necessarily have. So not only can we remove viruses, bacteria, and pathogens to a pretty low level. We can get, you can get 0.05, 0.02 NTU out of a media filter, which is kind of almost no particles coming out, right? So you can get excellent treatment with them, good pathogen removal, but you can do other things besides filter with a granular media filter. You can let them go biologically active, and that can remove some TOC, and that can help you with disinfection byproducts. You can potentially use them for manganese removal, and depending on if we build a new structure or how we retrofit existing ones, you could put a layer of activated carbon on the top, and you can combine kind of GAC adsorbers with filtration. The downside is that they tend to be larger footprint and bigger infrastructure. So you're kind of trading off footprint for flexibility. We're also looking at membrane filtration. Membranes are kind of a new thing, but they're not that new anymore. They've been in service for 30 plus years. The big difference between a membrane and a filter is a granular media filter uses the chemicals that you add ahead of the filter in order for it to work. And a membrane is just a strainer. Basically, anything that's bigger than the little pores in the membrane is going to get held back, and anything that's smaller will go through. So the nice thing is, even if you completely mess up everything that's going on upstream of a membrane, you're still going to get high quality water out. The downside is with a membrane, if you mess up the chemistry upstream, you can start to lose production capacity. Most facilities that have membranes don't have that issue. They're highly automated, so systems are able to keep production up pretty consistently. Their production rate depends on temperature too, so we'll think carefully about system demand patterns and sizing for that. The other downside is you have a second waste stream with membranes, which is basically chemical cleaning waste. It's not hard to deal with. You can neutralize it and send it down the sewer, but it just adds a little bit of complexity. And it tends to be a lot smaller footprint. So we're considering both of those for this facility as part of our larger evaluation. How are we going to decide what we're ultimately going to go with? I'm just going to touch real quick on our alternative evaluation approach. So kind of based on this discussion, we're still in the process of defining specific alternatives, and what we're going to do is we're going to come up with a few process train alternatives for retrofitting the old plant or building a new facility. And then we're going to use something our like $1,000 words, multi-criteria decision analysis. But basically what we're doing is trying to figure out what's important to everybody, weight things by level of importance, and come up with a solution that hopefully everybody is happy with. So this is just an example of a couple things we're going to be considering, but big picture, we're going to be working with you guys, the stakeholders in the city, and whoever we can get input from to come up with what are the most important things for us. So obviously cost is going to be both capital and O&M are going to be a significant factor. Operability, provenness of technologies, not that we're going to look at anything new, life cycle costs. We're going to get feedback, we're going to take these and then put weights on them, because not everything's equally important, right? Like cost is going to be a big factor, regulatory compliance is going to be a big factor, but there's some things we have more flexibility with, like some things are going to be harder to build than others, so we're going to put some weight on that. But you know, if you're going to save $10 million and extend construction time by 6 months, you know, these are the kind of things that we're going to look at and kind of think through. Then we're going to take the alternatives and the criteria and then score each alternative with the weighted criteria and see what we come up with. And this isn't intended to be like you do it once, you get one answer, and that's what you go with. It's kind of starts the discussion. You see what results come out. If you don't like what they come out, you kind of reevaluate, well, what do we really care about? Like something as much of a priority as something else. So it's kind of an iterative, cooperative process, so we reach a decision that everybody is reasonably happy with.
If we do get down the road and compare the two options and decide that moving to a nice new site is most cost effective, is the way we should go, a big component of this study is what do we do with that existing plant? We need to find another beneficial use for it. We need to keep it kind of at the core of the city. Building's a historical icon. The city appreciates that. It really needs to be preserved and used in some way. So some options that we looked at, you know, there's different levels you could take it to. If we kept the plant at this location and went with new treatment, you know, membranes, that type of thing, it would free up existing space in the plant. So maybe we're guessing maybe like 25,000 square feet that would open up. Could we use that for something else is a question, you know, community use. If we were to locate most of the water treatment plant functions, the things you'd want to keep here are the pump room, the screen room, that equipment. That might free up to 50,000 square feet. Or we repurpose the entire facility. Some concepts we played around with initially here, repurposing that filter gallery is a beautiful space, right? Could you do a farmer's market in there, a Christmas market? Could you open it up as like a wedding venue? We'll look at some of those type of concepts. The big goals for the city here, it's got to be something that preserves that structure and benefits the community, but we're also looking at the cost, and the city's standpoint is it also needs to generate some revenue, right? This can't be we build a new plant and then this becomes a cost sink for the city. They've got to maintain that building's going to require maintenance forever. So something that generates revenue would be what we're looking for there as well. And then the last task 9, we'll put together a extensive report. We've been writing report sections for the things that we've completed so far. Those are done. So those will all roll into the final report. We will need to complete cost estimates for the preferred options to compare both capital costs, but also on that life cycle cost. And then, you know, kind of high level construction schedules, the preferred option. Let's figure out how long this is going to take to build.